Welcome back everybody to another lecture for our physics class. We're going to jump into chapter 13, part of unit 7 for real-time imaging. So what is real-time imaging? It's what you guys have been doing this whole time. Every time you're looking at the machine and you're moving your transducer around and you're watching how the image changes because you've moved the transducer somewhere, you're basically getting real-time imaging. You're getting what is as close to a movie, as close to real life as the machine can produce. And so with real-time imaging, we get to see as we move, as structures move within the body, are they moving appropriately? We get to see where we're headed with our transducer, and that's awesome. Because when ultrasound originally started, not as awesome. Early ultrasound originally required the sonographer to take this articulating arm. There's a picture of it here. So there's this arm here, right? And there's a transducer right at the end of it. And what the sonographer had to do was drag this back and forth along the body. So the sonographer was responsible for making the scan lines. So they drag this back and forth, back and forth, back and forth. And then the machine would process all of those scan lines and make one picture. And that one picture was it. And then if they wanted another picture, they started the whole process over, dragging the transducer back and forth along the abdomen. And so, because it would take, let's just say 30 seconds to drag it all the way across the abdomen, it was impossible to see moving structures. So this type of scanning was considered static scanning, impossible to see moving structures. Not like we can now with our real-time scanning. So now our modern machines fire off pulses, steers the beam a little bit, fires another pulse, steers the beam a little bit, fires another pulse, and all those pulses get created into one picture. And because those pictures get refreshed so quickly, our brain thinks that we're seeing things in real time. That's what gives us kind of the perception of having a movie or real life or real time imaging. Now I know that I have said this multiple times before. This is a chapter where all this really kind of comes to a head. Remember, we have our transducer. One beam is sent out. All of those echoes have to come back to the transducer before the next beam is sent out. All of those echoes have to come back to the transducer before the next pulse is sent out, and so on, as we move all the way across our field of view. The time it takes to make this pulse and then to make all the pulses all the way across the screen to get that one picture that we get, that happens so quickly that it happens again, so our next picture might show slightly different, and it happens again so quickly, so our next picture shows something slightly different. And it feels like it's moving right along with us. That's how fast all of this is happening. And I think it's really hard to conceptualize just how fast that's happening. But it is such a quick process that our brain doesn't even recognize that there's gaps in time in between each picture. And it's just an amazing, amazing tool that we have. So the rate at which the machine can refresh that picture gives the machine its temporal resolution. So temporal resolution is the accuracy at which moving objects are being displayed in their correct position. The closer we are to real life movement, the better the temporal resolution is. Temporal resolution is described in frame rate. So it's how many frames can be displayed per second. And because we are using that frames per second or events per second, we actually use hertz as the unit of time. So frame rate is measured in hertz. Frame rate is actually quite often displayed on our pictures. You'll see probably somewhere in the corner, you'll see FPS, frames per second, or you'll see FR. And then behind it, you should have a hertz value sitting there. And so we're going to talk in this lecture what changes the frame rate. And a better frame rate is a higher number. So our 20 frames per second, 30 frames per second, those are good numbers because the human eye can only recognize, I believe it's up to 20 frames per second. Anything less than 20 frames per second, we start to see those gaps in between. If you think about like stop motion photography where it kind of looks like things are moving around, but it's not quite seamless, it's probably because they just moved that structure a little bit more. And that's what's happening when our frame rate gets too low. And so let's go back to the whiteboard for this example here that I just want to put out there. So let's say you are sitting in class trying not to fall asleep and your eyes open up every few seconds. So your eyes opening up is your sampling time, right? So that's the time it took to create one picture. And so let's say you are kind of dozing off, you open your eyes and it is second hand's at noon. And then you kind of doze off for a second and the second hand when you open back up is at the 3. So 15 seconds has gone by. And then you kind of doze off and you open your eyes again and now the second hand is at the 30. So you've got a pretty good recognition of time that it has moved 15 seconds into the future every time you close your eyes. So you have a good perception of the real life that is happening. What if, though, you're keeping your eyes shut a little bit longer? So here we have our clocks. What if you open your eyes and the second hand is at noon and then you close them for a while, and let's say you close them for 45 seconds. So now the hand is over at the 9 o'clock and then you fall asleep again and 45 seconds later again you open them. Well, now the clock hand is down at 30 seconds. It almost is like time moved backwards. And that's because you didn't get the real life motion of that hand moving while your eyes were shut. And so that's kind of what's happening in our ultrasound machines. The eyes are shut, or the machine's eyes are shut, while all of those beams are being created and then made into our final picture. If the eyes have to be shut or the beams take a long time to make, we're going to miss some of the movement of the structures that we're looking at. So again, we're going to talk about what causes our eyes to be shut or what causes the beam to take longer to make in this lecture. So you want to be very familiar with those. So to define frame rate then, we define it as the number of frames or still pictures that the machine is able to create per second. The higher again that frame rate is, the more movie-like our pictures appear, versus a low frame rate, we're going to see kind of jumps or gaps within our pictures. And frame rate is going to be determined by 3 factors. I believe your book only lists 2, but I want you to know this third one because it kind of gets incorporated later, and I don't know why Edelman only said 2 to begin with. Anyway, frame rate is determined by 3 factors. The first one is that sound speed in the medium. We know that it takes a fixed amount of time for sound to leave the transducer, travel to a predetermined depth, and then the machine has to wait for echoes to come back from that depth. We know that the machine thinks all those echoes are traveling at about 1.54 kilometers per second, and so that is a fixed number. We can't do anything about how fast the sound is traveling in the medium. The second thing that affects the frame rate then is the depth of imaging, and that is controlled by you, the sonographer. The more depth you have, the longer that sound has to travel down to the depth and back up to the transducer. So that makes sense then that we can't display as many frames if we have more depth. Where shallow depth will improve our frame rate. And again, we'll go over all of these a little bit more in detail. The last factor that affects frame rate then is the number of pulses per picture. And this is typically also controlled by you. How many focuses have you put onto your picture? What is the line density? How wide is your sector? All of these things change how many pulses are needed to create one picture. A concept that we need to understand then about frame rate is that we have frame rate, And we know that that is events per second. How many frames per second can be created? That's our frame rate. But we also have an idea of, or need to have the concept of, how much time did it take to make that one frame? So we relate then frame rate and the time it takes to create one frame as two different periods or two different time considerations, and we know that they are inversely related. They work just like frequency and period in that they are reciprocals. So if the frame rate increases, then the time to create one frame must decrease. Same then, if the frame rate decreases, that's because the time it takes to make one frame has increased. So of course there's formulas that go along with this. These two formulas are going to help you with your workbook this week, so make sure that you have access to these to use them later. So it tells us that the time to make one frame, or T frame, multiplied by the frame rate is going to equal 1. And that's because they're reciprocals. Another way then to figure out the T frame then is the number of pulses per one scan line and multiplying it by the pulse repetition period. So let's go back to the whiteboard real quick here and run through some examples. Actually, we have some examples coming up on the next slide. I just want to run through the concepts behind these two formulas. So we have our transducer, and T frame is the time it takes to create all of these pulse lines. So that's our T frame. What was the time it took to make one picture? So say, I'm just going to put some numbers out there. These aren't ultrasound based numbers. Let's say it takes let's say it takes 2 seconds to make all of those pulses, that one frame. That means then our frame rate is 1/2 a second. It is the inverse of it. So remember, 2 times 1/2 equals 1. So our frame rate is 1/2 a second. We can only show half a frame per second. This probably wasn't the best example, but I wanted to show something that had numbers. Let's take a look at a different one, and I think I've got some more examples coming up here. I'm just kind of pulling these off the top of my head. Let's say that it took 1/5 of a second to make all of these lines come down and make one frame. That means if it takes 1/5 of a second to create one frame, that we can display 5 frames in 1 second. So the frame rate on this would be 5 hertz. Okay, so as the time it takes to make them decreases, that means we can display more frames per second. Now you'll be asked in your workbook then to use the second formula, which told us that T frame equals the number of pulses multiplied by the pulse repetition period. So say the pulse repetition period is 1/1000th of a second, and we have 3 pulses. 3 times 1/1000th of a second gives us 0.003 seconds to create one frame. That then tells us that the frame rate is 3000 hertz. Okay, so you will be asked to figure this out. I did give you the pulse repetition period for all of the ones that you have to figure out, but we could have gone way back to some of those formulas that we needed from before. Giving you a hertz, you figure out the pulse repetition period and then kind of plug everything in. But not the point of this. I just want to show that PRP will have an effect on your T frame. The number of pulses also has an effect on your T frame. That's mostly what this formula is showing us. All right, so let's look at those examples. So our first example says, if the machine takes 1/20th of a second to make a frame, then it can produce 20 frames per second. The frame rate is 20 hertz. If it takes only 1/60th of a second to make a frame, then it can produce 60 pictures per second, and this makes the frame rate 60 hertz. So let's take a look again back at the whiteboard, just looking at using our T-frame multiplied by frame rate equals 1. That's all we're doing for those examples. It took 1/20th of a second to make one frame. We know then that our frame rate is just the reciprocal of this, which is 20. So frame rate is 20 hertz. If we are given that the frame rate is 60 hertz, then to calculate the T-frame, again, we just put 1 over it, we make the reciprocal, we get that it's 1/60th of a second. So this should feel very similar to how we were figuring out frequency and period of a wave. So if you remember back to that other formula that I showed you, that T-frame equals the number of pulses multiplied by the PRP. What I want you to recall about PRP is that PRP has everything to do with depth, remember? The more depth that we have, the longer it took for pulses to leave and return versus shallow depth, right? So PRP has everything to do with depth. When we increase our depth, our PRP also increases. So if we look at imaging depth and the frame rate, what we will see is that in shallow imaging, so maybe like 2 centimeters, 5 centimeters, we're going to have a short go return time, which makes our T-frame shorter because those pulses can return to the depth and get back in a quicker amount of time. So it takes less time to make one picture. So it's a short T-frame. Because it's a short T-frame, we get high frame rate and we get superior temporal resolution. This is a big reason why if you are imaging anything that's moving, be it the fetal heart, the adult heart, we want our depth set just past the anatomy. You don't want extra depth when you are imaging moving structures, and that is because it'll degrade our frame rate. When we increase our depth, then we see a longer go return time, which makes our T-frame longer, and with longer T-frames we have lower frame rates, and that gives us inferior temporal resolution. That was falling asleep in class and closing your eyes for 45 seconds versus 15 seconds. We're going to miss parts of the real information. So here is another example kind of showing us again with the pulse repetition period and how that's going to affect our temporal resolution. So the first example tells us that an image is created from 100 scan lines. And because it has 100 scan lines, that means 100 pulses need to be sent out for each scan line. And this is assuming that there's only one focus per scan line. So 100 pulses are needed to make 100 scan lines. If the PRP is 1/1000th of a second, the T-frame then is 100 multiplied by that 1/1000th of a second, which gives us 1/10th of a second. The frame rate then is the reciprocal of the T-frame, so our frame rate in this example ends up being 10 hertz. Say the sonographer then reduces the depth to half of what it was. And so now the machine still needs to create those 100 scan lines with 100 pulses, but now the PRP is half of what it was, so it's 0.5 of 1/1000th of a second. And so if we do the math on that, plugging those numbers into our formula, we get that the T-frame now has reduced to 1/20th of a second, which increases our frame rate to 20 hertz. So when we decrease our depth, we decrease our frame rate, we decrease our T-frame, which increases our frame rate. And higher frame rate numbers are better. So we always want to set our depth down to the appropriate depth to see the moving structures. Now I had mentioned earlier that pulses per image and frame rate are related to one another as well. And I also had mentioned that that is something that you can control as the sonographer. So there are 3 things that are typically going to change the number of pulses needed per image. The first one is that each pulse line can only have one focus. So if you have multi-focus on, that's going to increase the pulses per line, which increases the pulses per image. Your sector size, so do you have a very wide picture, or have you narrowed your sector in to make it a smaller picture? Wider sector sizes require more pulses, which will then decrease your frame rate. The last thing that can increase your pulses per image then are the lines per angle of sector, which is also known as line density. So let's take a look at each of these a little bit closer. So remember again, each focus that you put on requires a new pulse because each pulse can only have one focus. So if you increase the number of foci for your image, you are going to degrade your temporal resolution. However, we know that with more focuses, our beam becomes narrow and that improves our lateral resolution. So this is an important concept for sonographers to understand. Do I want a really clear still image, or am I more interested in the movement of my structures? So just going back to the whiteboard here, we have our transducer. Say we have 3 focuses on our image. We are going to have a very thin beam that ends up coming out, right? We're going to have those 3 focuses in there. But to make that very thin beam, we've got to send 1, 2, 3 down that scan line. 1, 2, 3 down this. 1, 2, 3. 1, 2, 3 for each one going across. Now you can see that that would take a lot of time to make 150, 250 scan lines all the way across our image. We are going to miss moving structures within there. That would be opposed to a single focus, where now it's just steering and firing in new directions. It's going to make that one picture very quickly compared to the 3. So when you add foci in, you can get an awesome still picture. So maybe that's for your gallbladder, for your liver, for your thyroid. If you need to see something moving in here, if you need to see those valves moving in a heart, you got to get rid of some foci so we can see real-time imaging of those valves. So here we have an example. We have an image that's created with 100 scan lines, and the sonographer only has one focus set on the machine. This means that there are going to be 100 pulses needed to create the image. If the sonographer decides to add in 3 more foci, so now we're up to 4, but we still have 100 scan lines, now we need 400 pulses to create one picture. The difference of waiting of 100 pulses versus 400 pulses to be sent is huge when we are seeing structures move very quickly. We are going to miss some of that information. So the 100 pulse picture is going to be awesome for temporal resolution because we're going to see structures moving in real time, as opposed to the 400 pulse picture, which is going to see the frame rate drop. We're going to be missing information from the moving structures, but we'll get more detail in the lateral plane. So the 100 pulse picture has superior temporal resolution, where the 400 pulse picture is most likely going to have superior lateral resolution. You'll see these charts through your notes and in the book as well. I think they're very nice to kind of organize the information, what happens when we change parameters, what happens to resolutions, both temporal, lateral, spatial, and compare that then to what happens to the frame rate. So again, just to recap, single focus, there's only 1 pulse per scan line. We have a shorter frame rate, keyframe, which gives us a higher frame rate, gives us superior temporal resolution, but we're going to have worse lateral resolution. That's opposed to our multifocus, which gives us many pulses per scan line, which increases our T-frame, which then lowers the frame rate, giving us inferior temporal resolution, but better lateral resolution. Sector size also plays a role in how many pulses are sent out into the body. So when we are scanning and we have our sector, that's our picture, our field of view, we can actually change how wide our field of view is. Do we want it all the way open because we're looking at a large organ such as the liver? Or can we narrow that down because maybe we're only looking at the aorta and transverse, or maybe we're just looking at the common bile duct. Maybe we just want to bring that sector in. When you are scanning a smaller area, you do not need as many scan lines. So yes, a wider view does improve the amount of anatomy that we can see, but it's going to degrade the temporal resolution. So if we think about our picture, when we've got a really, really wide picture like this, say the structure that we wanted was here, we're going to spend all this time making pulse lines out here, then we're going to get into the area that we want, and then we're going to spend a bunch of more time getting the pulse lines out there. So a wider sector is going to take longer, it's going to have a longer T-frame, meaning lower frame rate. The opposite of that then is we can bring that sector in. And if this is our structure, remember it was out like this before, but now we're just using the scan lines for this small area. We can produce these fewer scan lines much quicker and have an improved frame rate. So here we can see in the example, if we use the widest field of view that maybe uses 100 scan lines, and we only have one focus set, we're going to need 100 pulses to create this picture. If we decrease the field of view where only 40 scan lines are needed to create the image that we're looking at, now we've reduced the pulses that we need down to 40. So it makes sense then that this picture will be made much quicker than the full field of view. So that is another reason why we tell you to decrease your depth to only the anatomy that you need, and then bring in your sector again to only the anatomy that you need. And this is especially true if you are imaging structures that are moving. So again, a nice little chart kind of describing everything that we've talked about. Narrow sectors are going to have fewer pulses per frame. Because of the lower pulses per frame, they are going to have shorter T-frames, which results in higher frame rate and better temporal resolution. Narrow sectors, though, don't allow us to see as much anatomy. So that could be a deterrent to having a narrow sector. Maybe we actually do need to see all of that anatomy. So that's a trade-off that you need to decide as the sonographer. The wide sector then will have more pulses per frame, creating a longer T-frame, which creates a lower frame rate and degrades our temporal resolution, but now we can see more anatomy. Line density is the last concept that we need to talk about in regards to how many pulses are created per image. Line density, however, though, is not a concept that you will have to deal much with other than knowing what it does in theory. So line density is the number of scan lines that are used to create an image. And you can adjust the line density of a machine, but it's usually buried into multiple selected fields if you can change it at all. So it used to be more of a customizable thing on older machines, because now the machines are so modern and so quick that the line density can just be set and can be awesome, and the machine can still kick along pretty well. Older machines, you really needed to optimize things, especially if you were looking at moving structures. So chances are you're not going to be able to find line density on your more modern machines. If you can, though, play around with it a little bit, see what it does to your frame rate. And that's going to be true for all of this stuff. I do highly suggest while you are in lab, take a look at something that's moving, even if it's just holding it up to the heart. You know that you can look at the heart from the subhepatic space, angle up towards the chest. Those of you who are in echo, you're looking at this stuff all the time, so I'm sure your lab instructors have been guiding you on how to get the best temporal resolution already. But you want to make sure that, find something that's moving, add some more focus in, see what happens to it. Increase your depth, decrease your depth, see what happens to those moving structures. If you can't find a moving structure, just look at what the frame rate is displayed on your screen. Remember, we want it to be around that 20 hertz level so we can see more of a seamless movie versus kind of something that's jumpy. But anyway, back to line density. So line density is a thing that we can change on some machines. You probably won't need to change it or see how to change it on newer machines, but it's still an important concept to temporal resolution. And that again is because it changes how many pulses are created per image. So if we have fewer lines creating our image, that is considered low line density, and that would be our scan B. And so we have just a few lines coming down to create this picture, and if we increase the amount of lines, then we call this high line density, and that would be our example in A here. But what we are missing out, if we don't have enough lines, then we are missing out on our spatial resolution. We are going to be missing details within our image. So we can see from example B, the low line density only interacted with one of these structures, and so we are only going to display one structure. Versus on the high line density, there was sound interacting with both of these reflectors, so now the machine can display both. So we have improved spatial or detail resolution when we have high line density, compared to better temporal resolution when we have low line density. And so this example shows us a nice way that you'll see any questions regarding line density kind of set up. I'm going to go to the whiteboard real quick here. All right, so we have our transducer and then we have our sector. And what you will see is they will call this like a 90-degree sector. And then it'll say there is one scan line per degree. So if there's one scan line per degree of this 90-degree sector, that means that there are 90 scan lines to create this image. As if it was 2 scan lines per degree, then it would be 180. Okay, so this just kind of sets it up for how many scan lines, what is the density of this image. So let's go back to our example then. So if we have a system set up with a 90-degree sector, and there is a scan line for every 2 degrees, so this is different from what we talked about a second ago. There's now a scan line for every 2 degrees. We have 90 scan lines multiplied by half, so we are creating a picture with only 45 scan lines. If we have 45 scan lines, then that means we have 45 pulses going out into the body to create one picture. If we adjust the line density to now say that there is 1 scan line per every degree, then we have 90 times 1 means we have 90 scan lines now, or 90 pulses. If we increase that again to making the system create 3 scan lines for every degree, then we are going to have 90 multiplied by 3, or 270 scan lines, which would need 270 pulses. So what we will see from this then is that our low line density, our first example here, is going to have superior temporal resolution because it has the fewest amount of pulses. However, the most detail or spatial resolution will be seen with this one because we're going to have those scan lines packed really close together so we can get a lot of detail from the image. So again, back to our chart, low line density is going to result in widely spaced lines, which reduces our spatial resolution, but because there are fewer lines, fewer pulses, that means that our T-frame is going to be short, our frame rate will be high, which gives a superior temporal resolution. Opposed or opposite to that, then we have the high line density, those are going to be those tightly packed lines. We get awesome spatial resolution, but because there's so many more lines, that means there's more pulses, which results in longer T-frames, lower frame rates, and inferior temporal resolution. So as you've seen, all the settings that we are able to control can improve our temporal resolution, but it's usually going to come at some sort of price of worsening another type of resolution, be it spatial resolution or lateral resolution. So it's really up to you. What do I want out of my picture? Am I more interested in getting a super image of something that's moving, where I can see the structures and how they're moving in real time? Or am I more interested in getting detail about maybe the wall anatomy of the heart? Do I want to see the details of the wall of the common bile duct? Or do I want to see how the gallstones are moving in the gallbladder? So what is the focus of your scanning? Is it to see moving structures, or is it to see detail? If it's to see detail, then we want those multifoci. We want more anatomy to be visible. We want high line density. Those are going to decrease our temporal resolution, but it's going to give us better spatial and lateral resolution. If we want moving structures, we're looking at a heart and we want to see how those valves are moving, we want to see how the walls are contracting, then we need to decrease our depth. We need to bring in the sector, just the anatomy that we're looking at, decrease the line density, not to the point that we're losing too much detail, but enough detail to improve our frame rate, and make sure that we only have one foci on, so we can get the real movement, real lifetime, real imaging of moving structures. So I think your workbook will bring you through a lot of these scenarios very well. The biggest thing that you need to keep in mind while you're working through these is what's improving and what is worsening. Am I getting better temporal resolution, or am I getting better spatial resolution? Am I getting better lateral resolution? And then to recognize that when you create more pulses for a picture, that's going to really bring down our frame rate. So just remembering that relationship: more pulses, lower frame rate; more depth, lower frame rate, because that comes back to PRP. So really read the chapter, focus on those main points, and the idea of temporal resolution, the more you play with it in real life and kind of practice it, I think it'll all come together really nicely.